All right, so welcome to Math 150 Multivariable Calculus. This is lecture 3. This is the last of our review classes, and then after this on Friday, we will start multivariable calculus in detail. And so you should have already finished reading a good chunk of chapter 10. You should have already tried a lot of the practice problems on integration and differentiation. The way I'm going to run things is if there's something you want me to do, let me know, talk to me, talk to the TAs. Otherwise, I'm going to assume things are good and we're going to move on. I'm not going to prove everything. What I'm going to try to do is prove enough things so that you get a sense of, okay, if I really wanted to make this rigorous, I see roughly how one will do this. And so we're going to continue reviewing Calc 1 and Calc 2 today. Okay, so the first thing is the definition of the derivative. And so the one I wrote on the first line is the one that you should be most familiar with. It's the limit as h goes to 0 of f of x plus h minus f of x over h. When h goes to 0, h is never equal to 0. It gets closer and closer and closer to 0. Why do we never want h to be 0? Yeah, we are not allowed to divide by 0. Now, it would be balanced by 0 in the numerator. 0 over 0 is one of those undefined items. But what we can do is we can look and see what do we get as we approach 0, as we get closer and closer to 0. All of the rules from calculus come from limits. And so to really put the subject on a firm foundation, we will have to talk about limits. As I mentioned before, in one variable calculus, it's really boring. I can walk in this direction. It's really not that exciting. In multivariable calculus, I start to have the opportunity of going in straight things like that. I can even start climbing on the tables and whatnot. Right? There's a lot more. I'm pretty sure we've not hit anybody good. There's a lot more you can do. I can move 2-dimensionally. I can move 3-dimensionally. And now for the limit to exist, that means a lot. It's not actually a very strong statement to say the limit exists here. Then we have the standard functions. The x to the n. Initially, you prove this only when n is a positive integer. We talked about the issues when n is not a positive integer. It's nx to the n minus 1. The derivative of sine and cosine, derivative of sine is cosine, derivative of cosine is minus sine. Remember with the phrase minus sine to remember which one has the derivative. This is only true in radians. And over here, we're assuming we have radians. This is one of the reasons why we use radians, because in radians, the sine and cosine, the derivatives are nicely linked. Then we have the exponential function, e to the x, its derivative is just e to the x. If I give you b to the x, there's this extra natural log. And in college, we write log b to mean the natural log of b. Okay, we don't really use log for the log base 10 because everything in calculus is nice to base e. You don't have to remember these extra factors. If you wanted to prove this, the proof, we're doing a little bit of algebra. B to the x is e to the x natural log of b, or e to the x natural log of b, if that makes you a little bit more comfortable. And now if I want to take the derivative of b to the x, I can use the chain rule, and I'll get e to the x log b, and then the derivative of x log b, and the derivative of that is going to give me a natural log of b. That's where this extra factor comes from. So this is a very common way to pass from knowledge of something we know to something that's close. If I know the derivative of e to the x, I can get the derivative of 2 to the x of 5 to the x or 7 to the x by just converting. Similarly, if I know the derivative of the natural log is 1 over x, then I know the derivative with any other base. Okay. All right. So there's a bunch of rules. All of these rules are essentially coming from algebra and limit laws. A lot of them are the no-duh rules. The derivative of a sum is the sum of the derivatives. Now you have to be careful here. This is for a finite sum. In mathematics, whenever you see an infinity, that's a warning sign. So if I give you an infinite sum, it may not be the case that the derivative of an infinite sum is the infinite sum of the derivatives. It may not even be clear that the infinite sum converges. And so one of the big themes of this course is talking about Taylor series, replacing complicated functions with simpler ones. And the hope is that the further down you go, the less effect the terms have, and you get a really good approximation by just looking at a few things. That's why we're going to start the course by talking about sequences and series. The next is the constant rule. So, whenever you do math, if you can tell a story, that's great. I was trained as a physicist, so for me, my stories often involve physics. F of x represents where I am. X is time. So if I'm traveling if my distance is scaled by a factor of 5, what should the difference in speeds be? 5 times. So that's why the derivative of a constant times a function is the constant times the derivative. Another way of looking at it is if I change from measuring things in yards to feet, first of all, you're like, why are you measuring things in yards and feet? Can anybody give me a reason? This time of year, there's at least a natural reason why you might measure things in yards and feet. Football, right? Okay, football, okay, that's reasonable to measure things in yards and feet. Anything of scientific importance, no. If you change from yards to feet, you're rescaling by a factor of 3. Your speed doesn't change, but the numerical value will change by a factor of 3. So when you're looking at things, always think of units. If my units are yards per second or feet per second, it's still the same motion. But the numerical value will be different, and it'll be different by a factor of 3. The next is the product rule. That's the first one where things are beginning to get interesting. If you had supreme power over the universe and you got to choose mathematics to get the laws of calculus, would this be your quotient rule? The derivative of a quotient is f prime times g minus fg prime over g squared. This is probably not how you would choose to create the universe. All right? Chain rule, g of f of x, then the derivative is g prime at f of x times f prime of x. The important thing to note is I'm evaluating g at f of x. So when I take the derivative, I've got to evaluate g prime at f of x. I can't evaluate it at x. G may not even make sense there. Maybe g is the square root function, maybe f is a squaring function, so maybe x is negative. I can't evaluate g at a negative number, but f of x makes it positive, so it's okay to define g there. So when I'm looking at the chain rule, I can't evaluate g prime at f of x. The hard part is remembering that there's the f prime afterwards. Then there's the multiple rule. This is actually a special case of the chain rule. It's the case when the inside function is just rescaled by a. And what this tells you is if I'm rescaling by a, my speed increases by a factor a. So think of it as time is flowing faster. So you're covering the same amount of ground in less time. And then the last is the reciprocal rule. This is another special case of the power rule, which is a special case of the chain rule. It's just the special case when n equals -1. You could also view the reciprocal rule as a special case of which other rule on this list? So which other rule is the reciprocal rule a special case of? Well, we just said it was a special case of the chain rule, but there's another one on the list that would work. If you want, I can write this in a more illuminating manner. And so, is it much easier to see it's the quotient rule when I write it like this? This is a huge theme in the course. Depending on how information is written, it's going to be easier to process or not. Eventually, I will bring in some Rubik's Cubes and show you how easy it is to mislead you. And I consider myself somewhat of an expert in how easily I have been misled by some cubes. And oh, that's what it is. So much of math, so much of science, so much of life is trying to figure out what's the right way to look at something. If I write this as 1 over f of x, oh, okay, well, then this is the quotient rule in the special case when the numerator is 1 and the denominator is just my function. So a lot of times I could prove all these rules directly, or I could start proving them and then getting other ones as special cases. So if I have the reciprocal rule and the product rule, I actually get the quotient rule. If I have the quotient rule, I can get the reciprocal rule from that. So what I'm going to do is I'm first going to give, actually no, before I give a proof of the product rule, let's try to experimentally discover the product rule. How many of you are taking an experimental science class with a lab? Mathematics can be an experimental science. I want to study a of x is f of x, g of x. And I want to figure out what is the relationship. Well, does it make sense that a prime should involve f? G, f prime, and g prime? Does it make sense that those should be the ingredients? So I need some functions such that I can take their derivatives and I can take the derivative of their product. So can someone give me two functions f and g, which I can differentiate, and I can differentiate their product? So what are some functions? Yes, x cubed and what else? Good, so x cubed and x squared. And so to save time, I'm going to do a little more generally. I'm going to say f of x is x to the n, g of x is x to the m, and then a of x is going to be x to the n plus m, where n and m are positive integers. So your case of 3 and 2 is just a special case of this. This way I can handle all positive integer exponents simultaneously. All right, what's f prime of x?
X raised to n minus 1.
And then g prime of x will be m x to the m minus 1. A prime of x will be n plus m x to the n plus m minus 1. I have to get n plus m x to the n plus m minus 1. And do we all agree that f prime, g prime should be my inputs? All right, well, if I'm looking at those as the inputs, how can I get, in a very natural way, x to the n plus m minus 1? Can somebody give me one way I can do that? So how could I get an x to the n plus m minus 1 from these inputs? And this has to work no matter what n and m I give you. Any thoughts? Yes?
So you multiply the n and x, right? By the x to the n plus n minus 1. And then you can like.
So which two functions do I multiply?
Sorry.
So I want to get an x to the n plus m minus 1 from f prime, g prime. How can I get an x to the n plus m minus 1 from f prime, g prime? What combinations could give that to me? Yes. Good, that's one way. And what's another way? Yeah, so if I look at f prime of x, g of x, plus f of x, g prime of x, it turns out that equals a prime of x. So when you do the algebra, you'll get n x to the n minus 1 plus m x to the n plus m minus 1 is n plus m x to the n plus m minus 1. Is this a proof of the product rule? No. But it gives us some feeling that maybe it's true and maybe this is the right combination. The other problem, of course, is maybe this is such a special case that we're not really seeing the full product rule, that maybe these functions are too simple. Well, fortunately, I have a PhD in mathematics. I know more functions. And so if I take f of x equals sine of x, g of x equals cosine of x, a of x is going to be sine x cosine of x. Does anybody know a nice way of writing sine x cosine x? Who remembers their trig? It's always dangerous. Where have you seen sine x cosine x in trig identities? Anybody remember? The double angle. So sine of 2x is 2 sine x cosine x. This is just 1/2 the sine of 2x. And so if we assume we know some trig, f prime of x derivative of sine is cosine of x, g prime of x would be minus sine of x, and then a prime of x would be 1/2 derivative of sine is cosine of 2x times 2. Now, if we look at f prime of x, g of x, plus f of x, g prime of x, okay, f prime g is going to be cosine squared x, f g prime is going to be minus sine squared x. Does anybody remember what cosine squared x minus sine squared x is? Nope, that's cosine squared x plus sine squared x. Even if you don't know your trig, the answer's on the board, right? We know the product rule. It's got to be cosine 2x. So this is just your cosine x plus x is cosine x minus sine x, sine x. This is another way to give evidence that the product rule is right. Again, this is not a proof, but whenever you're trying to do something in life, if you can check some special cases, if you can build some intuition, this is extremely valuable. We now have a sense of what the product rule should be and why we have these strange combinations. So now let's go through and actually see how you would prove it. So proof of product rule. So I'm going to let a of x be f of x, g of x. And so all of these proofs start off the same way. They start with the definition of the derivative. A of x is the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. What looks strange about this? Is this how you would normally write things? What do you think I'm about to do? Why is there this huge space? Yes. Do nothing, right? This is what your parents or families are paying a tremendous amount of money for. How should I do nothing? Should I add nothing or multiply by nothing? Why multiply? Add. We're trying to get something that looks like an f prime times g and something that looks like a f times g prime. Well, f prime is going to be f of x plus h minus f of x over h. So maybe if I subtract, actually, let's do it in a different color. If I subtract f of x plus h g of x, that's going to look like f prime times g of, oh, that should be g of x plus h. And then I'll add f of x plus h, g of x plus h. And so I haven't really done anything. And so now I'm going to break it into two parts. It's the limit as h goes to 0. The first part is f of x plus h minus, oh, sorry, I want this to be f of x, not f of x plus h. Sorry about that. And so it'll be f of x plus h minus f of x over h times g of x plus h. And then for the next one, each term has an f of x, and then I'll have a g of x plus h minus g of x over h. The first term is looking a lot like f prime times g, and the second term is looking like f times g prime. What I want to use now is the limit of a sum is the sum of the limits. That is true so long as at least one limit is finite. And I'll give you some caveats about that in a moment. So this is the limit as h goes to 0 of f of x plus h minus f of x over h. Limit h goes to 0, g of x plus h. And I'm using now the limit of a product is the product of the limits plus the limit as h goes to 0 of f of x. And then the limit as h goes to 0, g of x plus h minus g of x over h. What does this first piece go to? As h goes to 0, what does this first piece go to? Yes, that just goes to f prime at what point? At x. And what does the next thing go to? As h goes to 0, what does g of x plus h go to? So what will g of x plus h go to? As h gets closer and closer to 0, g of x plus h is going to go to g of x. And then the next one, as h goes, well, f of x has no h dependence. Right? No matter what value of h is, I give you f of x. What happens as h goes to 0? I don't really care what h is doing. I'm always getting f of x. And the last piece is just g prime of x. And so in mathematics, we put in a filled-in box. That means QED, Coravat demonstratum, that which was to be proved. It means we've now finished the proof. So this is a proof of the product rule. You know, we added 0, but we really got this by using limit laws. We used the limit of a sum is the sum of the limits. We used the limit of a product is the product of the limits. We have to be careful. So we're going to just do some limit caveats. The limit as x goes to 0 of x squared minus x, the limit as x, let's say x goes to infinity, x goes to infinity of x squared minus x squared, and the limit as x goes to 0, say x over x squared, and we'll do one more, the limit as x goes to 0 of x squared over x. What does the first limit equal? As x goes to infinity, x squared minus x. What does that go to? As x gets larger and larger and larger, what does x squared minus x look like? So let's put in some large values. If x is 1,000, x squared is 1,000,000. So you've got 1,000,000 minus 1,000. If x is 1,000,000, you've got 10 to the 12th minus 10 to the 6th. What does x squared minus x go to as x gets larger and larger and larger? It goes to infinity. Compare that to the limit as x goes to infinity of x squared minus the limit as x goes to infinity of x, which would be infinity minus infinity. We're not allowed to do infinity minus infinity. Which infinity is larger? Infinity minus infinity is one of those expressions we just can't deal with. Okay, so we'll have the no list. Infinity minus infinity is bad. What else would be bad? What else do you think we should not be able to do? Yes. Infinity over infinity. Anything else? Well, infinity plus infinity should be okay. If I'm giving you large and large amounts of money, and one of the other professors is giving you large and large amounts of money, life is good. If I'm giving you large and large amounts of money, and another professor is taking away large and large amounts of money, well, it depends, who's going at a faster rate. So infinity minus infinity is dangerous. Infinity plus infinity is okay. Yes. 0 over 0. And there's one other one. Yes. Nope, infinity over 0 we can actually make sense of. Because the dividing by 0 is going to make it larger and larger and larger. Infinity times 0. So one of my favorite questions is, in Star Trek, Kirk, Spock, McCoy, and Ensign Expendable beam down to a planet. And a little bit later, Kirk, Spock, and McCoy and a dead body come back up to the Enterprise. It's not good to be the red shirt on Star Trek when you go down. Anybody ever watch G.I. Joe? No one's ever seen the G.I. Joe movies or anything? No one ever dies in G.I. Joe. So you have all the bullets going everywhere and everybody lives. And so the question somebody asked me, this is the irresistible force versus the immovable object. What happens if G.I. Joe joins Starfleet and wears a red shirt and beams down with Kirk, Spock, and McCoy? The best solution I ever heard is he survives, but the Enterprise is destroyed because all the equipment can be destroyed. There are certain expressions we just can't make sense of. 0 times infinity. 0 is making things small, infinity is making things large. Which one is winning? We need to go through it slowly. If I look at x squared minus x squared as x goes to infinity, what should I get for that one? Yeah, because at every moment in time, it's perfectly balanced. So in that case, infinity minus infinity would be 0. In this case, it would be positive infinity. I can make infinity minus infinity anything I want depending on rates. What about x over x squared as x goes to infinity? What's this going to go to? Well, I've got 0 over 0. Let's actually tweak it just a little bit. I'll make it x cubed just to be a little bit easier. So as x goes to 0, x over x cubed is the same as 1 over x squared. What happens with 1 over x squared as x gets really, really small? Yeah, that's going to go to infinity. If I just gave you x over x squared, there would be 1 over x. It could be going to positive infinity if x is positive, negative infinity if x is negative. So I'll just make it this way to be a little bit nicer. What about x cubed over x? What does that go to? As x gets really, really small, what does x cubed over x go to? 0. And of course, if I gave you the limit as x goes to 0 of x over x, that would just go to 1. So 0 over 0 can go to many different things depending on how we're going. You've got to be careful. When we state the quotient rule, what must be true if we're going to work with the quotient rule? What must be true if we want to use the quotient rule? G of x is? G of x can't be 0 at the point where things are happening. We are not allowed to divide by 0. If the numerator is 0, then we've got 0 over 0, and there may be a way to make sense of it. And you might remember L'Hopital's rule, which is a great tool from calculus to make sense of issues like this. But all of these rules are coming from limit laws. And so over here, the purpose of this is to show you that when we have these dangerous expressions, I can get the limits to be whatever I want. So you can go through and you can use these techniques to prove all these different results from calculus. Well, okay, that's Calc 1. So Calc 1 is about differentiation. What's Calc 2? Integration. Calc 1 is trivial. Here are the derivatives of the basic functions. Here are the rules. If I give you any expression, I really can't stump you. I can make your life unpleasant. I've got decades of practice on this. Let's say I give you f of x is 3x squared plus the square root of cosine x plus 4x cubed to the 17. And then let's add x cubed and let's square that. Okay, I can write this as a of x squared. And so the first thing would then be f prime of x is just going to be 2a of x, a prime of x. And I just start doing it slow and slow and slow. Let's make things a little bit more painful. This is too easy. Let's put a multiplication sign here. Okay, so now I know it's 2a of x, a prime of x. And I know a of x is 3x squared plus the square root of cosine x plus 4x cubed to the 17 times x cubed. What do I do now? Product. So you keep pushing down and you keep making it simpler. And so I can write this as b of x times c of x. And a prime of x is b prime of x, c of x, plus b of x, c prime of x. So I'm stating the rule I'm going to use, and I can write b of x equals blah, b prime of x equals blah, c of x equals grr, c prime of x equals, and I just put that all together. which ones of these is going to be nice? Well, C and C prime isn't so bad. There's no real reason to do that. This is just x cubed 3x squared. And then to get b prime of x, what would I do for that? Power rule. So whenever you hear the word of, think chain rule. Power rule is a special case. I've got, when you hear 2, you should think power rule. So later on, we'll have the square root of cosine x plus 4x cubed. And when I hear the of, that's going to be a hint that I'm going to want to use the chain rule. This is not a pleasant problem, but this is a trivial problem, especially for computers to do. All you have to do is just go through it carefully and not make a mistake. The more you write things down, the longer it's going to take you, but the less likely you are to make a mistake. I've been doing this so long that I can do most of this without writing all these things down. I know immediately it's going to be 2a of x, a prime of x. I don't have to write let n equal 2. I'm going to do the power rule like that. But if you want to, by all means, feel free to do that. So this is how you would attack problems like this. Okay? I can't give you a differentiation problem that can stump you. I can easily give you an integration problem that can stump you. It is inexcusable in this class to get a differentiation problem wrong, because you can just work through it slowly. Completely acceptable not to know how to do an integration. That's okay. What is not okay is to get an integration problem wrong. You should at least know you're wrong. You don't have to know how to do it, but you have to know you're wrong. How can you know if you got an integration problem wrong? Do it backwards. What does that mean? Take the derivative. So if you have a proposed answer, well, I can just check the derivative. So in computer science, you have this beautiful classification of types of problems. And there are some problems that are very hard to solve, we believe, but they're very easy to check and see if an answer is right. Factorization is one of those problems that's quite interesting. To date, no one has publicly given a good, fast algorithm to factor numbers. But it's very easy to check and see if somebody has a correct factorization. What do you do to check and see if someone has a correct factorization? Multiply the numbers. I claim this is a factorization of this number. No, it doesn't multiply to that. Oh, crap. Okay. No. So when I give you an integral, you can always check and see, did you get it right by taking the derivative? Okay. So let's keep going. So all the rules for integration come from the rules for differentiation. The sum rule is really nice. The derivative of a sum is the sum of the derivatives. The integral rule is very similar. The integral of a sum is the sum of the integrals. Same thing for the difference. Same thing for the constant multiple. The chain rule, the product rule, these become far more interesting. So let's look at the integral of f of x, g of x prime dx. So can anybody tell me what function has derivative f of x, g of x? So what function has derivative f of x, g of x prime? F of x, g of x, right? No, it could also be the plus c, but that's fine. So this would just be f of x, g of x, right? We know how to integrate that. I'm asking you, what function g of x prime? F of x, g of x. Its derivative is the derivative of f of x, g of x. Let's expand this. By the product rule, we know this is the integral of f prime of x, g of x plus f of x, g prime of x dx. So the integral of f prime of x, g of x dx would be the integral of f of x, g of x prime dx minus the integral of f of x, g prime of x dx. And this piece here is, of course, just f of x, g of x. Could I switch things? And instead of doing it this way, could I have the prime on the g here and the prime on the f here? Yeah, that just changes which one I move over to the other side. I have a choice. I have two possibilities that are essentially the same. And the reason is, well, look, f of x times g of x is the same as g of x times f of x, right? I can multiply in any order. So whatever rule I get for differentiation, it should be symmetric under switching f and g. And so I could do it either way. I could have f of x g prime of x, or I could have f prime g of x. It doesn't really matter. So now I'm going to make a little notation. I'm going to let u be f of x. I'm going to let dv be g prime of x dx. And then v would be g of x. And this is basically saying, dv dx is g prime of x. And then du is f prime of x. So du dx is f prime of x. And this is going to give me the integral of u dv is equal to uv minus the integral of v du. That's where this rule comes from. This rule comes from the product rule. And I'm just letting u be my f of x and my dv being g prime of x dx. This is one of the most useful integration results we have. And it essentially comes from the product rule. And the hope is that instead of doing the integral u dv, instead of doing the integral fg prime, it's actually easier to do f prime g. So this records the exchange rate in passing from fg prime to f prime g. Has anybody, oh, this is interesting. Anybody ever gone to, say, Canada or Mexico? Have you bought anything there? Did you use local currency? So you have to convert your dollars to Canadian dollars or to pesos. Nowadays with credit cards, it's not as necessary to do that. You just have a conversion. That's what we're doing here. We're converting from integrating fg prime to integrating f prime g. And here's the cost. The banks often hit you with a little bit of a conversion cost. They don't do this, out of the goodness of their heart. The cost, however, I'm not really worried about paying this. I can evaluate u and v. That's not a big deal. If I had to integrate u and v, I may not want to do that. But this is a really cheap conversion cost. So let's try to do an example. So the hardest part when you do these is to figure out what are the choices of u and v. So let's say I give you the integral of x cosine of x dx, and I'll go from 0 to pi halves. So I have to decide, what do I want to be u, what do I want to be dv? There's for the most part two choices here. Do I want u to be x, or do I want u to be cosine of x? Do I want dv to be x dx or cosine x dx? Any thoughts as to which way we should do this? What do you think? You have a 50-50 chance. Yes. So I like making ux because now when I take du, I just get dx. I'm lowering the degree of x. If I just had to integrate cosine of x, I can integrate cosine of x. Not a big deal. If I did it the other way, if I made dv be x dx, then v would become x squared over 2. So I take a hard problem and I make it worse. So if you try to do this integration by parts and the problem is getting worse, what should you do? Yeah, try the other one, right? When there's not that many choices, okay, if something's not working, put it off to the side, try something else. If that's even worse, curse a little bit and then go back to what you tried first. And if that's still bad, then try to find something else. All right, so I'll have dv be cosine x dx. So what function has derivative cosine? Sine. So I would now get the integral from 0 to pi halves of x cosine x dx. would be uv, so it'd be x sine of x at 0 and pi halves minus the integral from 0 to pi halves of v du sine of x dx. All right, well, when x equals pi halves, I get pi halves times the sine of pi halves, which is 1. So this is just going to be pi halves. When x is 0, I get 0. What function has derivative sine of x? So what function has derivative sine of x? I want the integral of sine of x. Okay, well, then if it's a negative cosine, then let's put that negative sign in with it. And so that's going to give me a cosine of x at 0 and pi halves. Cosine of pi halves is 0. Cosine of 0 is 1. So this would become pi halves minus 1. Always ask, is this reasonable? What can you tell me about the function x cosine of x between 0 and pi halves? In the interval from 0 to pi halves, what's true about x cosine of x? Can somebody give me a lower bound for that function? So if you think back to the circle, we're in the first quadrant. This is, x equals 0, x equals pi over 4, x equals pi halves. What can you tell me about x cosine of x? What kind of number is it? Can you give me a lower bound? Yeah, it's never going to be negative. So we know it's at least 0. We could do some real work and try to figure out the largest value it can take, or we can just do something fast and dirty. I vote fast and dirty. What's the largest x can be from the interval 0 to pi halves? What's the largest cosine x can be in this interval? So what's the largest cosine of x can be between 0 and pi halves? 1. So the largest this could be is pi halves. It's actually overkill, because when x equals 0, cosine of x is 1. But when x gets large, when x is getting close to pi halves, cosine of x is getting close to 0. This is going to overestimate. So I know the area is somewhere between 0 times pi halves is thus equal to the integral, is thus equal to the maximum value pi halves times the length of the interval pi halves. So I know the answer has to be somewhere between 0 and pi squared over 4. This answer is between 0 and pi squared over 4. With a little bit more work, I could get a better estimate for how large x cosine x could be. So how would we find the maximum value of x cosine of x for 0 less than equal to x less than equal to pi halves? What do I do? So how would I find the largest value of x cosine x for x between 0 and pi halves? This is a calculus question. How do I find the largest value? What do I look for? What do I do? Yes. You are the first person in years to say check the boundaries. Normally I run and I ask people, where am I running fastest? And I start accelerating as I get to the blackboard and I slam in. And so I really appreciate the fact that you said check the boundaries. When you're trying to see where are you largest, we talked about how the sign of the derivative tells you if you're increasing or decreasing. Well, if I'm at the boundary, it doesn't matter if my derivative is positive. I can't go any further, so I can't take advantage of that. I have to check the boundaries. Okay, so let's check. So when x equals 0, we get 0. When x equals pi halves, what do we get? We also get 0. So it's got to be the critical point. We need the derivative of x cosine of x to equal 0. So what's the derivative? It's going to be 1 times cosine of x plus x, and the derivative of cosine is minus sine of x equals 0. Okay, so that's cosine of x is equal to x sine of x. So now we get 1 equals x tangent x. So we need to solve for that. The whole point of this is to show you that even with simple functions, we can quickly come up with hard problems to solve. Trying to solve 1 equals x tangent of x, that's not easy, right? We can try to approximate that. And then once we get that, we get, say, some value, maybe say, x critical point satisfies 1 equals x tangent x. So then the maximum value is x critical cosine x critical. And then if we feed that in, we would get a better upper bound for what things could be. Okay. But again, the point here is we actually need better techniques than what you've learned in high school to solve problems like this. And so we will talk later in the semester about how would we actually approximate an answer to this. And this will be another great way of seeing sequences and series. All right, so the last thing I want to do today for the review is substitution. We will probably not do any partial fractions or very little partial fractions in this class. This is the least favorite technique of integration from students. The only people who don't list it as their least favorite are the ones who've been so traumatized that they forgot they learned it. And as soon as you remind them of it, after they start screaming and calm down a little bit, go, oh yes, I hated that. I'm not going to be doing that. The goal of this class is not to give you painful integrals and derivatives to do. It's to talk about how do we use our calculus knowledge to solve problems we care about. And so everything comes from differentiation. So if a of x is f of g of x, a prime of x is f prime of g of x times g prime of x. So if I give you the integral of f prime of g of x times g prime of x dx, what would that integral be? It's just f of g of x. So the whole point is, can you recognize when I give you something of the form f prime of x g of x times g prime of x? You have to recognize that. So for example, let's say I give you the integral of x e to the x squared dx. If I want to try to solve, well, let's let g of x be x squared. G prime of x would become 2x dx. Well, sorry, I guess so. G prime of x would just be 2x. G prime of x dx would be 2x dx. If I let f of x be e to the x, f of g of x would be e to the x squared. F prime of x would be e to the x. F prime at g of x would be e to the x squared. I can recognize this as, oh, okay. I basically just put a factor of 2 here and a 1/2 and just move this over here so that this is just 1/2 the integral of e to the x squared times 2x dx. So this would just become 1/2 e to the x squared. Another way that we do problems like this, which I think is a little bit easier sometimes to follow, is we have the integral of x e to the x squared dx. We do what's called u substitution. And basically, u is our g of x. So let's say I want to integrate from 0 to 20. So we try u is x squared. So du would be 2x dx. So x dx, which is what we have, would just be 1/2 du. Now, x goes from 0 to 20. Where does u go from if x goes from 0 to 20? So if x goes from 0 to 20 and u is x squared, what's the range of u? 0 to 400. And so now we get the integral from 0 to 400. I'm going to write u equals x e to the x squared becomes e to the u du with a 1/2. And then this would just be 1/2 e to the u at 0 and 400. So just be 1/2 e to the 400 minus 1/2 e to the 0. You don't have to put u equals down here. You could just go from 0 to 400. I like putting the u to remind myself I've changed variables. All right, so this finishes the review of Calc 1, Calc 2. There's a lot more stuff in Calc 1 and Calc 2 than we can do in just 2 days. We've got to start the real new material. We'll review some additional material as we start seeing its analogs in Calc 3. So we'll be doing sequences and series on Friday. All right, have a good rest of the day.